There we are. All right, so give me just 1 second to get the document camera set up and to get you guys pulled up in WebAssign, and we'll get started. Okay. Our textbook, this is section. Right. Just those, though. Yeah, okay. Numbers, plane curves, and parametric equations. This is it. All right, beautiful. So, good afternoon. Oh shit, DocCam software crashed. All right, sorry, give me just 10 seconds more. Started. This week we're going to be talking about parametric equations, parametric curves. All right. So there's that. Let's get the screen share going. There we go. All right. So welcome to the last big topic in MAC1147. Normally, I would end up spending a considerable amount of time at the end here also talking about conic sections and ways to interpret those things geometrically, and we do have next week for that. But this week's focus is going to be just 8.4, or is it 8.4 and 8.5? Yeah, just 8.4, which is the section on parametric equations. Before we dig into this, I know everybody's dying to know what's going on with the exam. I haven't finished grading them. My goal is to get them back to you by this Tuesday, that is by our class time tomorrow. Unfortunately, the way we're doing things here just takes much, much longer than grading a paper test does, because I have to write out the problems and the feedback and then scan all of that stuff up one person at a time. And to do it fair, I have to go through and do one problem at a time rather than doing one person at a time. So it is very time consuming, but my goal is to get everything back to you by tomorrow. So I'm about halfway through, and I think I can probably finish them up tonight, but I will let you know as soon as that stuff is ready. You'll see the grades in the grade book. And then if you look at the comments, when you go to your grade book and scroll down to a particular assignment, there's always a comments section. That's where I will paste the link for you to look at the feedback that I gave you for each question. So with that in mind, I do want to start on this new topic of parametric equations. It's a big change of pace for us. Last week, we spent all week working with polar coordinates. Parametric equations are not a different coordinate system, but it is a different way of thinking about curves in the plane. So kind of what's going on here is that we've seen many curves which arise as graphs of functions. Like where y is a function of x. You may also have seen, we haven't talked about them much in this class, but curves, which are graphs of functions. Instead of y being a function of x, sometimes x is a function of y. So for a curve like this, where y is a function of x, that graph has to pass the vertical line test, you know, something like sine or cosine or any polynomial. All of these satisfy, you know, y equals f of x for some function f. On the other hand, there are also things like this that definitely don't pass the vertical line test. But if you turn your head sideways, they do. So here, x is a function of y. But many curves don't look like either of these. Many curves, for instance, the unit circle, don't pass the horizontal or the vertical line test. And what we want to start doing is finding ways to think about those curves using function notation, because it's super duper useful when analyzing curves, especially when it comes to calculus. Presumably that's what everybody here is gearing up for. But in a parametric curve, so a curve given as the graph of parametric equations, of a set of parametric equations, doesn't have to have, so need not or needn't have y as a function of x or x as a function of y. So you could have something truly crazy, you know, something that does some bizarro stuff like this. And the trick or the idea is that instead of giving one formula where I tell you how x and y are related to each other, I give you two formulas where I tell you how x and y, each on their own, change over time. And we usually think of these as paths of particles that are in motion. So I would give you two equations. One is going to look like x equals some function of time. I'll call it x of t. And y equals some other function of time, y equals y of t. And these two are totally independent from each other, apart from both containing the variable t. And then I'll also usually give you a time domain. I'll give you some t values that we are considering, where maybe a is less than or equal to t is less than or equal to b. So the point where we start is the point associated with time t equals a. We usually consider the variable t as being time. So this would be x of a, comma y of a, and we call this the initial point, or the starting point. And then I think of a particle as walking along this path as time advances. So here, this doesn't pass the vertical line test. It doesn't pass the horizontal line test. There is no way to get this curve as the graph of some function where x is a function of y or where y is a function of x. But if I think of both coordinates as just changing with time, rather than changing dependent on each other, then I can think of those guys each as being functions. And I think of this path as being a path that's traversed by a particle or a little ant walking around in the xy plane. These arrows that I'm drawing in right now show what's called the orientation of the curve. So we started down here at our smallest t value. This is the point associated with t equals a. And we're ending up over here. This would be x of b, comma y of b. And this is called the terminal point. And it's associated with t equals b. So that's the that's the basic gist of what we're going to be talking about when we talk about parametric equations. We're going to be trying to graph curves where instead of having a direct relationship between x and y, we have a relationship between x and t and a relationship between y and t. But notice that neither of these axes are the t-axis. This is the x-axis, this is the y-axis. T doesn't show up in the geometry anywhere. So that's the basic idea. You think of this particle as moving around as t runs from A to B. So here's time t equals A, and it moves. Here's time t equals a little bit further. Here's t a little bit further. Here's t a little bit further. X is changing with t. Y is changing with t. But neither of them have a direct relationship to each other, or at least they don't necessarily have a direct relationship to each other. Sometimes they will, sometimes they won't, but you're not guaranteed a direct relationship. Does the basic concept seem to make sense? Do you have any questions about the definition or how this contrasts with the picture we're a little bit more used to, where one variable is a function of the other?
So basically so you still have an x and a y value on the thing, and the t is basically showing the direction it's going, or is it like what would t be doing?
So t we think of as a parameter, and that's why we call them parametric equations, because they're given in terms of this extra parameter called time. So imagine I told you that I've got a guy, he's going to start out right at the corner of Archer Road and Southwest 34th Street. And instead of telling you, you know, he's going to, I could describe his path a number of different ways. I could say as he walks west along Archer, he's also going to start going north along, you know, whatever that cross street is there through Butler Plaza. Instead of describing what he does north-south in terms of what he does east-west, I could tell you he's going to walk east at 1 mile per hour and he's going to walk north at 2 miles per hour. And that would also describe his path, where I tell you the left-right separate from the up-down instead of having those two related to each other. That's the idea, is that I tell you the left-right separate from the up-down. And then the picture is what you get when you combine both of those. And we think of t as being the time over which the particle moves through this path, or over which the guy walks this path. Does that help?
Yeah, so if like instead of saying you're at point x and y, you could say you're moving at t and those both equal x and y?
Something like that. I think you're getting close, and I think a concrete example will really help. So let's take something whose graph should look familiar to us once we get to it, and see if we can't discover this on its own. So I'm going to give you the parametric equation x of t equals t squared minus 3t. So this is our first example. We're going to sketch the curve defined by the parametric equations x of t equals t squared minus 3t, y of t equals t minus 1, where let's say -3 is less than or equal to t is less than or equal to +3. Let's do it like that. So I tell you what x is doing over time. I tell you how the graph is moving left-right over time. And I tell you how the graph is moving up-down over time. But I don't tell you how those two are related to each other. So if I make a table here, just like we do when we're learning how to graph functions in any other setting, if I don't have any idea what to do, I make a table. My variable is now t. T is my independent variable, and x and y both change in their own way as t changes. Now my t's here are only allowed to run from -3 to 3, so I'll plug in the integers between -3 and 3. And for each t value, I'll get an x and a y. And that will be the point on the graph associated with that t value. So first, let's go ahead and fill out this table. When t is -3, this guy will be 9 plus 9. Is that 18? Am I seeing that right? Yeah. And y here would be -3 minus 1 is -4. When t is equal to -2, this guy will be 4 plus 6 is 10. And this guy would be -2 minus 1 is -3. When t is -1, x would be 1 plus 3 is 4. And y would be -2. When t is 0, x of t is equal to 0, and y of t is equal to -1. When t is 1, 1 squared minus 3 is -2. And 1 minus 1 is 0. When t is 2, this would be 4 minus 6. Oh, did I do this computation correctly? 1 minus 3, yeah. And then this is going to be 4 minus, did I do that right? 1 minus 3, -2, right? Yeah.
Okay. -2.
Thank you. Yeah, sorry. My brain just farted here because I'm surprised to see this x value showing up twice in a row like this, right? So 4 minus 3 times 2 is 4 minus 6 is -2. We'll see what happens. And then here, this is going to be 2 minus 1 is 1. And then here, when t is equal to 3, we'll have t squared is 9 minus 3 times 3. That's going to be 0, isn't it? Yeah, okay. And then when t is 3 in this, we'll have 3 minus 1, which is 2. So each one of these rows gives me an ordered pair. This row gives me the ordered pair 18, -4. This row gives me the pair 10, -3. This row gives me the pair 4, -2. This row gives me the pair 0, -1. This row gives me the pair -2, 0. This row gives me the pair -2, 1. And this row gives me the pair 0, 2. So if I try to graph all these ordered pairs, let's see what shape we get. So I'm going to give myself lots of space. Looks like my y values don't get too huge. They run from -4 up to 2. But my x values do get quite large in the positive direction. So let's give lots of space there. And I'll just go ahead and mark this as 20. So halfway is 10. And then we'll kind of eyeball things as needed. I'll call this 1, 2, 3, and 4 on the y-axis. And so this would be -1, -2, -3, and -4. And now let's just start plotting these pairs. So 18, -4, that's out here, right? If this is 20, 18 is like a little bit before it. This would be 15, 16, 17, 18, somewhere around there. So we're going to come down to about here. This is the ordered pair 18, -4. This is the one associated with t equals -3. So I'll put a little t equals -3 next to him. Then when t is -2, I have the ordered pair 10, -3. So that's 10, -3. And this is associated with t equals -2. So here's the idea. My particle starts off here. This is the smallest time in my domain, -3. And then between time equals -3 and time equals -2, he moved from here to here. Now, if I turn the clock forwards 1 more second to time t equals -1, where is he? Well, time t equals -1, he's at 4, -2. So if that's 10, then this would be 5. So 4 would be right before 4, -2, somewhere right around here. And this is associated with time t equals -1. We keep going. When t is equal to 0, we have the point 0, -1. So this is the point 0, -1. And it's associated with t equals 0. So my particle so far started here, and it's moved along some curve to get here. Now I keep going. At time t equals 1, we're at -2, 0. So let me see, where would -2 along this axis be? Well, -5 would be like right here. So -2 should be like right here. So here's the point -2, 0, and it's associated with the time t equals 1. So far we've moved along this curve like this. Now we go to time t equals 2, and we're at -2, 1. So we're up here. And this is associated with time t equals 2. At time t equals 3, we're at 0, 2. And we could make maybe one more row on this table to help us see a little better what's going on. When we get to time t equals 4, what's going to happen? Well, this will be 16 minus 12, which is 4. And this would be 4 minus 1, which is 3. So we'll have the point 4, 3 on the graph. So where is that? Here's 5. So here's 4. Here's the point. So this is this point. Here's the point 4, 3 associated with the time t equals, 4. So look at these points. What kind of shape do we think these are forming? Big fat points here. Should be 4, 3. Yeah, it should be symmetric with this. My art is bad and I feel bad. This is a big old parabola. It's just sideways. Right? Now, since my time domain ran from -3 to 3, I really shouldn't have any of these parts. This is my initial point. And this right here is my terminal point. So my particle started here and it moved along this path like this. Or if you think of it as a little ant walking around on the page, he started over here, he walked around like this, and then he stopped here. And the trick is to just think of x and y as being independent from one another, just connected to this variable t. And the reason I'm scratching these last bits out is because I'm only interested in what happens up to the time t equals 3 seconds, because that was the time domain that was specified for this example. Okay. So my initial point, my ant started right here. As time increased, he walked over this way, swung around, walked over here, and then he stopped there at time t equals 3. If you like, let me see here. Desmos, I believe, has a pretty nice setting to play around with parametric equations. Points, no. Yeah, let's see this. Oh, no, those have too many examples built in. So let's just start a fresh graph. So I'm going to switch my screen share now. Over to here. And I'll just go ahead and enter the curve that the equations that we were given. T squared minus 3t. And y of t equals, oh, here, I think I should enter this as an ordered pair actually. So I'll enter the x coordinates, t squared minus 3t. And then the y coordinate, which is t minus 1. And I let t run from, we said, -3 to 3. And you see here this curve, right? This sideways parabola, just as we found. If I let t run out a little bit further, you'll get more and more of the parabola. So let's think of it like this for now. Let's think of it like this. My particle starts all the way out here at this point, right? My initial point. And then it moves along this path. So here's t equals -3, -2, -1, 0, 1, 2, 3. So it moves along this path, starting at this initial point and ending at this terminal point. The way to graph this in Desmos, what I did is I put it in as an ordered pair, where the x equation went in the first slot, where x normally goes, and the y equation went in the second slot. And you can check your work like this. I encourage you to work with Desmos and play with it. If you want to kind of picture the ant walking, here's what he did from time t equals -3 to -2. He walked from here to here. And then he walked to there, and then to there, and then to there, and then to there, and then there, and then there. Or no, he stopped here, right? Yeah. So this is the basic idea behind graphing parametric curves. But it's going to take quite a bit of practice, and there are some tricks I can show you. So that's my goal today, is to give you guys a little bit of practice, show you some of the kind of classic examples, and then to also show you 1 or 2 tricks that can be helpful in figuring out what the graph of a parametric set of parametric equations is going to look like without necessarily making the table. Just like we did in polar coordinates, right? We first get used to working with these in the table, and then we try to get comfy anticipating or finding some other way to see what the graph would be besides like the painstaking process of punching out a table. Before I take that away, any other questions or thoughts? Open to all comments and anything like that about this example, or regarding the definition, or how we're coming up with graphs, that sort of stuff. You see how I added these arrows to show the orientation of the curve, to show what direction we're walking along it in? That's important. Every time you graph one of these parametric curves, it's crucial that you show the orientation. So y'all feel pretty comfy with where this graph came from? Let me show you how we could have discovered this graph differently. Instead of making a table, sometimes we can get a normal Cartesian equation from the parametric ones by doing what's called eliminating the parameter. So for the problem we just looked at, I could eliminate the parameter t by taking either of these equations and solving them for t. This one is easier to solve for t, and then plugging that in here. So for example, what we just looked at, I'm going to write it without the of t notation. I had x equals t squared minus 3t and y equals t minus 1. If I solve y equals t minus 1 for t, I get, well, I just add 1 to both sides. Y plus 1 equals t. Now plugging that in to the equation for x, I find x equals y plus 1 squared minus 3 times y plus 1. And this now doesn't have any t's in it. Somehow it carries all the information that these two separate equations carried, but it doesn't have any t's in it. That's, for us, as we're getting used to this stuff, a nice thing. You might have an easier time graphing something like this, especially after you simplify a little bit. This is y squared plus 2y plus 1 minus 3y minus 3. And if I put all this together, what is that? I have y squared minus y minus 2, which is clearly a sideways parabola. If I gave you y equals x squared minus x minus 2, you would immediately recognize that as being a parabola. Here, the x's and y's are just swapped, which means you have to rotate your head 90 degrees to the side. If I switch back to Desmos, and not thinking about parametric anything, I just enter this equation, x equals y squared minus y minus 2. You see, the red graph is a part of the blue graph. The blue graph is the whole parabola because it doesn't have any time domain restrictions. But the red graph and the blue graph live on top of each other. They're the same shape. So we could have discovered the shape of the curve from that previous example by eliminating the parameter t instead. So which is a sideways parabola. We could factor this to find the y-intercepts. We could put it into vertex form by completing the square to find the vertex. All the things that we did way back when we worked with quadratic functions at the beginning of the semester, we could do with this to learn about these parametric equations. And this is called eliminating the parameter. You go from 2 equations, each involving the variable t, to 1 equation only involving the variables x and y. Another classic example of this let's say like this.
Now, since you guys are not just a pre-calc class, you're a pre-calc trig class, this example should be screaming some stuff at you. I tell you x is cosine t, y is sine t, and immediately your brain goes what? Starts with a U, ends with knit circle. Right? The unit circle is the set of all points x comma y in the plane such that x is the cosine of something and t is the sine of that same thing. And if we eliminate the parameter here, I can't do it by solving one of these equations for t. That game won't work now because neither of those is easy to solve for t. If I did like this using the inverse cosine or this using the inverse sine, I immediately run into domain restriction issues because those functions are not well defined everywhere. But what I do know is that cos squared of t plus sine squared of t is always equal to 1. So here, that means, well, cos squared, that's x of t all squared plus y of t all squared equals 1, because x is cosine t, y is sine t. And then if I just drop the of t notation, I get x squared plus y squared equals 1, which is the usual Cartesian equation for the unit circle. But just like in that first example, I didn't get the whole parabola, right? The red and the blue sat on top of each other, but the blue extended far beyond the red. Here, I'm not guaranteed to get the whole unit circle because t is only allowed to run from 0 to pi. So when I go to graph this, I know it's going to be a part of the unit circle. So I should insert that here, right? A part of the unit circle. And to figure out exactly which part and how much, I should graph the initial point. So when t equals 0, what point are we at? We're at cos 0 comma sine 0, because x of t is cosine t. Cosine of 0 is 1. Sine of 0 is 0. So my initial point is right here. That's the point associated with t equals 0. And now I'm going to graph also the terminal point when t is equal to pi. We're at cos pi comma sine pi, which is -1 comma 0. So I know my terminal point is over here. Which is the point associated with the largest time value in my domain, the largest t value I'm allowed to use. So I either have like the upper half of the unit circle or the lower half of the unit circle, or I walk all the way around the unit circle and then I walk around halfway again to get here. And we have to ask ourselves, which of these do I really have? To sort it out, think about each of these functions on their own. The cosine function starts off decreasing. Picture a cosine wave. You start at the top and you go down, right? From your perspective, you start at the top and you go down. Then you come up, then you go down. The sine wave starts off at 0 and goes up and then down and then up. So as t starts to increase from 0, my x values should start coming in and my y values should start going up. So what does that look like? If I come in and up at the same time, that means I'm going to do something like this. So I know that's how my curve is starting off. And if you plot a few more points, you'll find up here is the point associated with t equals pi over 2. Down here is the point associated with pi. In other words, in this very special example, and this is not always the case, t is the same as theta. And you trace just the upper half of the unit circle. If I wanted to come up with a set of parametric equations that describe the whole unit circle, I could use these same equations, cos t for x and sine t for y. I just need to let t run from 0 to 2 pi instead of from 0 to pi. Does that make sense? So just like in the last example, we can eliminate the parameter to come up with a Cartesian equation, a regular xy equation. Here we recognize the xy equation as being the equation of the unit circle. And so I know that my graph will be at least a part of the unit circle. I plot the initial point and the terminal point to figure out which part. And to make sure I'm graphing it right, maybe I plug in 1 or 2 other points, something like that. Or think about what the functions are doing as far as increasing and decreasing is concerned. That's what I like. I like to say, oh, well, the y value should start off increasing because y is sine of t, and I know that the sine function starts off going up. So my y value should start off going up. Questions on this example?
So to get the number 1 that you needed, you just squared everything?
Sort of. So I recognize that with x as cosine and y as sine, if I squared them and added them, I would get 1. So this recall is a mathematician's silly trick for saying like, here's a useful thing that I pulled out of my ass. I'm more or less just pulling this out of my ass. Like I'm saying, oh, well, I know cosine and sine happen to be related by this equation. And since x is cosine and y is sine, that tells me that x and y will be related by the same equation. So that if you're looking for like strategies, things to think about if you're trying to eliminate the parameter, if both parametric equations are algebraic equations like these guys were, then you're going to want to solve one of them for t and plug that into the other. If both equations are trigonometric and you're trying to eliminate the parameter, you're going to want to kind of force a trig identity in there somehow. And this was the simplest way to force a trig identity in there that would relate the equation for x with the equation for y, which is my goal.
Got it.
All right, workable answer? Okay. Oh, I never even noticed this thing. Cute. All right. So let's look at 1 or 2 more little examples like this. This really is all that I plan to drop on you guys for this week. So this week will be a fairly light homework week. The book's examples are not a lot of fun. Yeah, no, let's not do that. Let's do something like, let's see if we can graph these curves, or this curve. It's one curve, right? But I'm getting it from the set of parametric equations, x of t equals e to the t, and y of t equals e to the negative t. So again, I need to find some way to relate x to y if I'm going to eliminate that parameter, if I don't want to have to make a table. And there is a nice relationship between them here. One option is to go ahead and solve this for t. I could start with x equals e to the t and solve for t. So how would I solve that equation for t? Does anybody remember this from when we talked about exponential functions?
Is it a logarithm?
Yeah. Yeah, to solve this equation for t, I would take the natural log on both sides. So I have ln x equals ln of e to the t. What is the ln of e to the t?
T?
Yeah, exactly. So that's it, we're done.
I was gonna say some shit because I remember when you said
Tempting.
e to the t is just that stuff. So yeah, t.
It's true. If this was ln of e to anything else, we would just have that thing. If this was ln of e to the dog shit, we'd have dog shit. But since it's t, we just have t there. So then I know that t is equal to ln x, since t equals ln of x, y, which is e to the negative t, is equal to e to the negative ln x. Can I simplify that at all? So I'm in good shape now, right? I have y equals e to the negative ln x. I have eliminated the parameter t, but I don't know what this graph looks like off the top of my head. That's a weird looking thing. So is there any way to make this thing look less weird? Is there any way to simplify e to the negative ln of x? We're going to need one of our rules for logarithms. This one. I can bring that negative out front inside as a power. So e raised to the negative ln of x is the same as e raised to the ln of x to the negative 1, because I have this property of logarithms. And then again, just like we said here, the ln of e to some stuff is always just that stuff. Well, this is e to the ln of some stuff. That is also just that stuff. So this is the same as saying y equals x to the negative first. In other words, this graph I'm looking for is a portion of the graph y equals 1 over x, right? X to the negative 1 is the same as 1 over x. So I know what 1 over x looks like. That's a rational function. It has a vertical asymptote at x equals 0, horizontal asymptote, y equals 0, and so on. So in quadrant 1, I have a part that looks like this. And normally over here, I'd also have a part that looks like this. But as t runs from 0 to infinity, e to the t doesn't actually run over all real numbers, does it? What is e to the 0?
1.
Yeah. So while this is the whole graph of y equals 1 over x, the only portion I'm going to be looking at is from here. Oh, I should have a less than or equal to if I'm going to include the 0 here. So my initial point is x of 0 comma y of 0. And I'll write it like that first so we can see where it's coming from. X of 0, like Stephanie just said, is e to the 0 is 1. And y of 0 is e to the negative 0 is also 1. So this is my initial point. And then what do you think my orientation is? Am I walking up this way, or am I walking out this way, or doing something else? And why? Any thoughts?
Are you moving away from 0?
We are moving away from 0. And one nice way to see that is that x is e to the t, which is an increasing function of t. So as t gets bigger, e to the t gets bigger, right? E to the t is an increasing function. Picture the graph of e to the t. That's that normal exponential graph. It gets really big really fast. So as t gets bigger, my x's are getting bigger. That means I'm walking this way, right, towards larger and larger x values. So I'm going to throw away all this shit. And I never even touched this branch. This is really my curve. If I was going to draw this curve really carefully, I would say, okay, here's one, and my graph looks just like this. This is the graph of that parametric curve. Right, just that portion. I don't have a terminal point. This is associated with t equals 0. I don't have a terminal point because t here was allowed to run all the way out to infinity. So I just have an initial point. And my orientation is like this. So I've got a little object, and it's moving along the graph y equals 1 over x, starting at the point 1, 1, and just kind of rolling downhill. And it goes on and on and on like that forever, right? It approaches this asymptote and just goes on and on and on like that forever. Does that make sense? Do we feel kind of comfy with the idea of eliminating the parameter and sketching the graph of a parametric curve? One of the other skills that we care about in this setting is going the other way. So what about doing the opposite? Taking a known graph, taking a known function, and writing a set of parametric curves or a set of parametric equations which give that graph. So suppose this is called parametrizing the curve. So taking something that's not in parametric form and putting it into parametric form is called parametrizing or parameterizing. So I'd say parameterize the graph of y equals, let's do ln of x from x equals 1 to x equals e squared. So I know what the graph of ln x looks like. I have this vertical asymptote down here, and then I kind of curve over, and I keep going up, but I go up real slow like that, right? This is y equals ln of x. Here's the point where x is equal to 1. It's 1, 0. And e squared is going to be way out here somewhere. And the graph does keep going up. It just goes up very slowly. So maybe here is e squared. And we have this point right here, which is e squared, 2. So I want to find a parametrization of this curve, really just this portion from here to here. I want to find a set of parametric equations, which when graphed, both as functions of time, independent of one another, will generate that picture. If the curve you're given has one variable explicitly solved as a function of the other, then this is easy. The standard parametrization for a curve where y is equal to f of x is you just let x of t be t, and then y of t is going to be f of t, where f is the original function that related x to y. So this is the tool we're using, and the result that we get when we apply it to this particular problem is, so to parametrize y equals ln x from x equals 1 to x equals e squared, we write just like this says, x of t equals t, y of t equals f of t, where f of x is the function relating x to y. Well, the function relating x to y here is the natural log. Y is the natural log of x. So if x of t is t and y is the natural log of x, then y has to be the natural log of t. And then the trick is just to make sure you choose the correct time domain. With the standard parametrization, your time domain will always be the same as the x domain that you wanted to play with, because x of t is just t. So here I would say 1 is less than or equal to t is less than or equal to e squared. And if you want to check, we can bring Desmos back. I can graph t comma ln t, where t, close this, is allowed to run from 1 to e squared. Right? And just like we wanted, we see this portion of that curve. If I graph y equals ln x, you see that that's the same curve, just that the parametrization only gives us the portion that we said we wanted, the portion from x equals 1 to e squared. If I wanted to get the whole thing as a parametric curve, I could let t run from 0 to infinity. Oops, I gotta have this a strictly less than. Here, let me say 0.001 out to 1000, right? And then you get the same thing as you get when you graph y equals ln x. They match exactly. So this is called the standard parametrization. And what we wanted was the graph of the natural log from 1 to e squared. And the standard parametrization did the job for us. We were able to get a set of parametric equations that just gave me the portion of the curve I wanted by using this trick, where you just let x be t, and then you let y be whatever you get when you plug in t for x. It's a nice trick. It's a useful trick. One of the reasons we do this is for the purpose of physics. It's very often nice to decompose a moving particle into its x and y components separately. If you can tell me what the horizontal direction is doing with time, and you can tell me what the vertical direction is doing with time, then a lot of things having to do with figuring out forces in a particular direction becomes nicer, simpler, easier. Another reason is purely geometric. There are some calculus problems, like finding the length of this curve from here to here, that are much, much nicer expressed in terms of parametric equations. Like the formula to find that length is horrible if you treat y as a function of x. But if you treat both of them as functions of time, then it can be seen as a consequence of the Pythagorean theorem, a squared plus b squared equals c squared. And come see me in Calc 2, I'll show you. The last reason is in Calc 3, you're going to want to integrate along a curve. And I know you don't know what integrate means, so that's not really a useful thing to say. But there are a lot of calculus operations that are performed along curves. And most of those calculus operations require decomposing that curve into its x stuff and its y stuff separately. And that means parametrizing it. It means writing x as a function of t and y as a function of t without the two of them directly related to each other. So this business of parametric curves, primarily useful thinking about moving particles. Anytime I want to track the motion of a particle through two-dimensional space, it's easiest to do by giving the left-right stuff and the up-down stuff separate from each other, just in terms of time. And then the other reasons relating to future calculus classes, of course, are very important to students, so don't eschew those. How do we feel about this? We got time for another example if you'd like to look at one. There's one extra fun example that I'm going to hide from you today. We won't play with it right now, but we will play with it tomorrow. I don't want to spoil it for you. But if there's anything here that you guys would like to look at a little bit more closely, or you'd like to ask or talk a little bit more about, I would be happy to do so. Not so bad, right? Really not so bad. Learning how to parametrize a curve is one of those sticking points. So when you get to Calc 3, especially if you take it with myself, Sarah George, Aaron Degan, Brandy Cook, any of the kind of larger or more commonly referred to calculus professors at this college, being able to parametrize a curve is a big deal. It's something that will give you shit for if you don't remember how to do it. So please remember how to do it. It's important and it's not too hard. Remember the standard parametrization for a function, just let x be t, and then plug in t for x to get y in the original function. Going the other direction, I give you a set of parametric curves and I ask you for a graph, you can make a table. If you don't know what else to do, making a table is a fine idea. You can use, I'll show you something nifty in the calculator here. Oh shit, it's not there. Here, give me 10 seconds, pull this up. Motherfucker, where are you? So, if you happen to have a TI-80 whatever, there's a way to ask this thing to graph parametric curves for you. So I hit the mode button there, same place you would go to change from degrees to radians or radians to degrees. You come down here, you've got normal function mode. You've got, this is a polar mode. You can use this thing to graph polar curves, or you can select pair for parametric. If you do that, then when you hit y equals, instead of having y1, y2, y3, you have x1 as a function of time and y1 as a function of time. So for example, I could enter here t and the natural log of t. And then if I graph this, I'll get the graph y equals ln x, but only for those specific t values. I could enter here cos t. Oh, shit, sorry. Some of these things I can type, some of them I can't. And here, sine t. And I'll get some portion of the unit circle. So all of these are good tools to play around with for getting comfy with this idea of parametric curves. They're not too bad, they're really not. And I think you'll have fun doing it, start thinking about these things as particles in motion. And I encourage you to do so. The homework in WebAssign this week is not going to be extra brutal, it'll actually be pretty light. Because all you're doing is graphing, and WebAssign can't really ask you to do a whole lot of graphing by hand. But then next week we're going to talk a little bit about conics, and then we'll be done, guys. We will be done with MAC1147. The last exam for this class is just going to cover the polar, parametric, and conic section stuff, and it's going to be a like take-home project type thing. It's not going to be the normal like timed thing, but then there will still be the final exam. The final exam is going to be in The final exam is going to be in WebAssign, and it's going to be run much the same way that exam 3 ran. Exam 4 is going to be that take-home exam that I just mentioned, and I will give that to you guys on the last day of class. So I think our last class meeting, it's in the syllabus, is next Thursday, a week from this Thursday, the 23rd, I believe. I could be mistaken, but I believe it is the 23rd. So I'll give you the exam 4 take-home on that day, and it will be due on the day of the final. So you'll have to get it back to me at the start of the final exam. And it's all going to be online. So I'll send you guys a PDF. You will write out your answers, and then you'll scan them and submit those to the assignment in Canvas, which I will grade for exam 4. And then the final exam will run the exact same way exam 3 ran. You're going to take the test in WebAssign. You're going to write out thorough, neat solutions for every single problem. The WebAssign stuff will count as the true, false, multiple choice portion of the test. And then your written work will be graded as the free response portion. Any questions for me, either about the content or about tests or classwork, how things are going to go, anything like that?
Not for now.
All right, everybody else feeling pretty good? Okay, good. Then that's where we're going to leave it for today. I'll have your exams back to you tomorrow. If I get them done sooner, I'll put the grades up in Canvas, but you can expect them back to you tomorrow by class time. And then we'll pick it up from here with some more parametric graphing examples. There's one fun example, if you want to Google about it, it's called a cycloid. It's pretty neat. It's a little bit complicated, so I wanted to save it for tomorrow. But yeah, that is it for today, guys. I will see you tomorrow.
Thank you.
Of course, yeah. Have a nice afternoon.